In general, it may not be possible to give a description of the algebra generated by a collection of subsets of a set X. In a special case, when the starting collection C is at least an semi-algebra of subsets of X, it is possible to describe the algebra generated by it, and that is our next theorem. So, we want to describe the algebra generated by a semi-algebra. The theorem states the following: let C be any semi-algebra of subsets of a set X, then f of C, the algebra generated by C, is given by the following collection. So, it is a collection of all subsets E in X such that E can be written as a union of sets, finite number of sets Ci's, I say 1 to n, which each one of the elements Ci is in the collection in the semi-algebra C, and these Ci's are pairwise disjoint. So, what we are claiming is that the algebra generated by a semi-algebra is nothing but the finite disjoint union of elements of C. And we have seen an illustration of this in the previous lecture when we described C was the collection of all intervals, and we took f of C, the finite disjoint union of intervals, and showed that that was an algebra. So, that is a typical model example or illustration of describing the algebra generated by a semi-algebra. So, let us prove this, that the algebra generated by the semi-algebra is nothing but as described above. So, let us given C a semi-algebra, f of C, the algebra generated by C is equal to all sets such that I can write E as a finite disjoint union of elements belonging Ci's belonging to C. And note this square bracket square union means that the sets involved are pairwise disjoint. So, let us observe first a few things. First of all, C is a subset of f of C. That should be obvious because every set in C is union of itself, single. So, E has a representation as union of itself. So, only one set is involved. So, E is a subset of, and that implies that the empty set and the whole space belong to f of C. So, as a consequence, it implies the first property required for f of C to be an algebra and generated, we will see it later. So, second thing, we are trying to show that f of C is an algebra. So, first property we have checked. Let us take a set E belonging to f of C. That means, that implies that E can be written as a finite disjoint union Ci I equal to 1 to n, where Ci's belong to f of C. But recall saying that Ci's belong to C, recall saying that Ci's belong to C and C is a semi-algebra. This is important, implies by the property of the semi-algebra that each Ci can be written as Ci complement, can be written as a disjoint union of elements of C again. So, let us write it as Aij j equal to 1 to some Ki, where Aij's belong to C again and they are disjoint. So, this together with the representation for this implies, so look at E is a union of Ci's, each Ci complement is equal to this. So, that means first of all E complement can be written as intersection of I equal to 1 to n of Ci complement, and each Ci complement is a finite disjoint union. So, this is I equal to 1 to n of finite disjoint union j equal to 1 to ki of aij, right. So, here we have used the property, namely that E complement by De Morgan laws is intersection of Ci's, because E is union of Ci's complements, and each Ci complement being an element of the semi-algebra can be written as a disjoint union of elements Aj. So, that is the representation. Now, we use the fact that intersection distributes over union. So, what kind of this set is? This can be written as a union, okay, of finite number of sets which will involve Aij. So, sets of the following type: intersection A K L, because when I distribute it over, I will be getting one set Aij and some other set AKL, and this intersection of that and unions of those. And these unions, so these sets belong, each one of them belong to C. Why does it belong to C? Because the collection C is a semi-algebra, both of them are elements of the semi-algebra, so this intersection is an element of the semi-algebra. And these sets are pairwise disjoint, because if I, K, J and L, if any one of the pairs is different, then those sets will be disjoint. So, I can say this is a disjoint union of sets of the following type, where I belong between 1 and Ki, K between 1 and some K, some index, and J and L between 1 and L. So, basically what we are saying is E complement can be represented again as a finite disjoint union of elements of C again, and that is following because of the fact that E complement, which is a union of sets, is an intersection, and that is intersection of distributive property and this. So, it's because the indexes involved are so many, it is difficult to write all these things, but it should be clear that E complement is a finite disjoint union of elements of C. Okay. So, that means E belonging to f of C implies E complement belong to f of C. And let us look at the third property, namely if E and F belong to f of C, does this imply that E intersection F belong to f of C? Well, that should be obvious, because E belonging to f of C means E is a disjoint union of some Ai's 1 to n, Ai's belonging to C, F is a union of some J's 1 to m of some sets Bj's, J equal to 1 to m, where each Bj belong to C. So that implies, so let us conclude from here. So, E intersection F will be equal to this union Ai's intersection of union Bj's, I equal to 1 to n, j equal to 1 to m, and once again using the distributive property, we got this intersection of Ai's intersection Bj, I and j. So, the intersection and each one of them belongs to C. Okay. This is union over I and j. So, let us this by the distributive property will be union over I and j of Ai intersection Bj, and these elements are elements of C, because C is a semi-algebra, Ai belong to C, Bj belong to C, and these are again disjoint because they are Ai and Bj, right. For disjoint pairs, for different pairs they will be disjoint by the property that these unions are disjoint. So it implies that E intersection F also belongs to F of C. So what we have shown is the following, namely if I look at C is any semi-algebra, if I look at this collection of then subsets which are finite disjoint unions, then this includes C and is an algebra. To show that it is algebra generated, we have only to show that if A is an algebra and A includes C, that should imply A includes F of C. Well, to prove that is obvious, because let E belong to F of C, but that will imply that E is a disjoint union of elements AI, where AI's belong to C and C is a subset of A. So C is inside A. Okay. So that implies that E is a union of some elements in A and A is an algebra, that means A belongs to A, E belongs to A. So hence F of C is a subset of A. So what we have shown is that this collection F of C of finite disjoint unions of elements of the semi-algebra is indeed the algebra generated by the semi-algebra. So we are able to describe completely the algebra generated by a semi-algebra. And note one thing, we have described the algebra generated by a semi-algebra explicitly, and as remarked earlier that the algebra generated by a semi-algebra is described, but in general the algebra generated by any collection of subsets, we cannot describe it explicitly. One may not be able to say what are the elements of that algebra generated by collection of subsets. So that is not possible always. It is only in the case when it is a semi-algebra C we start with, we are able to describe the algebra generated by it. So we have looked at a semi-algebra, we have looked at an algebra of collection of subsets of Ax, and then we have looked at the algebra generated by a semi-algebra of subsets of X. Next, we go to the next level of collection of subsets which are slightly stronger, and that is called the sigma algebra of subsets of X. But before that, probably let us look at another property, namely how do we generate more algebras or sigma algebras out of a given collection. So let us take C, any collection of subsets of a set X, and let E be a fixed set in X. Let us write C intersection E to be the collection of sets of the type C intersection E, C belonging to C. Note that C intersection E, C is a collection of sets and E is a set. So C intersection E is just a notation for all sets of the type C intersection E, and note these are all subsets of the given set X. So the claim is that given any collection C and given any set E, let us look at C intersection E and generate the algebra by this collection of subsets of. So F of C intersection E is same as the algebra generated by C intersected with E. So this is a very useful thing of restricting, in some sense restricting the sigma algebras, or restricting the algebras. So what we are saying is C any collection of subsets of a set X, E contained in X fixed, define C intersection E to be C intersection E where C belongs to C. So what are these sets? So note that it is C intersection E. So this is a subset of, so this is a collection of subsets of the set E. And now I can look at F of C intersection E. So what will be F of C intersection E? It is the algebra of subsets of E generated by C intersection E, generated by the collection C intersection E, and the claim is that f of C intersection E is same as, you first generate the algebra by C. So, this will be the algebra generated by the collection of subsets in C, okay, the subsets of X. So, this is algebra of subsets of X, take its restrictions to E, and that is same as this. So, this is the theorem, or this is the result that we say is true. So, let us prove this. Okay. So, to prove this, let us first observe, note. So, first of all, we observe that C is contained in f of C, right. Given any collection C of subsets of a set X, f of C is algebra generated by C. So, by the very definition, C is a subset of f of C. So, that implies that C intersection E is a subset of f of C intersection E. Is that clear? So, if I take a set in C intersection E, okay, that is going to look like, okay, that is going to look like here, C intersection E, and C belongs to E. So, that is also an element in f of C. So, is f of C intersection E. So, this is, okay. So, let me write, because if A belongs to C intersection E implies A intersection E belongs to C, okay, which is in f of C, okay. So, and A belongs to, and A is an element in C, okay. So, the C intersection E. So, A belongs, that means A belongs to C. So, this is in C, so that is in f of C. So, implies this is an element of f of C intersected with a E, and that is precisely the meaning of this. So, we have got C intersection E. Because of this, this is true. And now, let us observe that f of C intersection E is an algebra of subsets of E. This is an algebra of subsets of E. Why? Obviously, empty set belongs to this, because empty set can be written as empty set intersection E. So, that belongs to f of C intersection E. And second, now note, these are subsets of E. So, what is the whole space? That is E. So, E is equal to E intersection E, okay. So, that is X. So, that is X intersection E, okay, and that belongs to f of C intersection E, okay. So, I can write E as X intersection E. X is an element of f of C and E is here. So, that belong to f of C. So, the empty set and the whole space, that is E, they belong to this collection. What is the second observation? So, let us look at the second observation from here. Let us take two sets. So, let us take two sets A and B belonging to f of C intersection E. That means this A is equal to, okay. So, if A belongs to, that means C intersection E, that means A can be written as some set, let us write G intersection E, where G belongs to we are looking at f of C, and B is also in this. So, B is written as some H intersection E, where H belongs to f of C. So, that implies A intersection B is written as G intersection H intersection E, okay. And now, G and H both belong to f of C. So, this belongs to f of C, and that is in A. So, implies A intersection B belongs to f of C intersection of E. So, and finally, let us look at third. If A belongs to f of C intersection E, that means A can be written as some G intersection E, where G belongs to f of C. So now let us look at A complement, but keep in mind the A complement is in E. Okay, so this is nothing but G complement intersection E. See, this complement is in E. We are taking the complement inside the set E, okay, because we are looking at the collection of subsets of E. So this belongs to f of C intersection E. So what we have shown is that C intersection E is subset of this, and this collection is an algebra, so that implies the property. So this implies, so let us observe, so this implies that the algebra generated by C intersection E is a subset of f of C intersection E, right? Because this collection is inside this and this is an algebra, so the algebra generated being the smallest must come inside. So we get this property. Now we have to prove the other way inequality. So claim that f of C intersection E, okay, is a subset of f of C intersection E. So this is what we have to prove. So to prove this, let us define a collection A to be all sets A contained in X such that A intersection E belongs to f of C intersection E. Okay, let us look at this collection A. Note, C is contained in A, right? That is obvious, because if I take an element in C, then that set A intersection E belongs to C intersection E, which is inside this, right? Because A belonging to C implies A intersection E belongs to C intersection E, okay, and which is inside f of C intersection E. So C is inside A, okay. So if A is an algebra, what will this imply? C is inside A is an algebra, that will imply f of C is inside A. But what is the meaning of f of C is inside A? That means for every element f belonging to f of C, okay, if we look at f intersection E, that is belonging to f of C intersection E. So that means that f of C intersection E is f of C intersection E is a subset of f of C intersection E, right? So to complete the proof, we only have to show that A is an algebra of subsets of, okay, A is an algebra of subsets of X. So now let us look at this and show this is an algebra of subsets of the set X. So let us start observing. So we want to show this is an algebra of subsets of a set X. So to show that, let us observe 1. Empty set belongs to A because empty set intersection E is empty set which belongs to f of C intersection E. The whole space X belongs to A because the whole space intersection with E, which is E, that belongs to f of C intersection E. Keep in mind, this is the algebra of subsets of E generated by this collection. Secondly, let us take a set E belonging to A, that implies, okay, that let us take a set G belonging to A, that means G intersection E belong to f of C intersection E, and this is an algebra of subsets of E. So this will imply that the G complement intersection E also belongs to f of C intersection E, because it is an algebra of subsets of E, so its complement should also be inside that, and that implies that G complement belongs to A. So G belonging to A implies G complement belongs to A. And finally, let us conclude that if G and H belong to A, that imply that G intersection E and H intersection E belong to f of C intersection E, and that implies G intersection H intersection E belongs to f of C intersection E, once again by the fact that this is an algebra, f of C intersection E. Once again the fact this is an algebra. So the collection A of subsets of X is an algebra, includes C, so that must include f of C, and that proves the theorem that the algebra generated by a collection C, that is f of C, when restricted to A, the set E is same as first restrict the collection by which you are generating and then restrict and generate. So what we are saying is, given a collection C of subsets of X, if we restrict the class C to the subsets of E and then generate the algebra of subsets of E, that is same as first generating the algebra and then restricting it, that class of sets, to that of E. This is going to be very useful later on when we want to restrict collection of sets to subsets of it. Okay. So let us just conclude what we have done today. We started with the recalling what is an algebra, what is a semi-algebra, what is a algebra, and then we started by observing that in general, if a collection C of subsets of a set X is not an algebra, we can always generate an algebra out of it. That means we can show the existence of a smallest algebra of subsets of the set X which includes this collection C, and basically that is the proof is by showing that if I take the intersection of all the algebras which include C, then that is the smallest one. And that also had the important property, namely observation, namely intersections of algebras is again an algebra. So that was a crucial property, a crucial observation that helped us to prove that the intersection of all the algebras that include C is also a algebra, and that includes, because of the intersection, so it has to be smallest, and hence that is the algebra generated by it. And then we gave examples of how to find algebra generated by a collection. For example, if you take singleton sets of any collection of for any set X, then the algebra generated is the collection of all sets which are either finite or their complements are finite. And in general, if C is a semi-algebra, then the algebra generated by it is nothing but the collection of all finite disjoint unions of elements of that semi-algebra. So thank you. So we'll continue next time.